Okay, so then now we start with the last talk of today. So please, the time is yours.
Okay. Shall I start?
Yeah, sure.
Okay. Okay, thank you very much for inviting me to give these lectures. It would have been, of course, much better if I were able to actually physically go to Cairo. I'm sorry I cannot do that at this moment, but I am hoping that I will be able to come to visit BUU sometimes pretty soon. So this set of lectures deal with two important aspects in the quantum many-body systems. The first is quantum quench, and it's the interplay of this with another important aspect, which is critical phenomena. I will not assume too much of background to be able to understand these lectures. And since these are short lectures, I will not do too many details, but I will sort of guide you to more literature, which will provide a lot of the details and the references. So let me first introduce the problem of quantum quench. The problem relates to a time-dependent Hamiltonian. So typically you have a parameter in the Hamiltonian, which is sometimes called a coupling, and that parameter depends on time in a fashion which I will now indicate. The dependence on time has the property that if I draw this as a function of time, at very early times, this parameter goes to some constant value lambda naught, and it does whatever it does. And again, at late times, it asymptotes to some other constant value, which I'll call lambda 1. And the question is the following. So given some nice initial state, which could be, for example, the ground state. So for example, the ground state of the Hamiltonian, when the value of this parameter is lambda 0, we want to figure out properties of the state at late times and in fact we would also like to figure out some details of the time evolution. As in all problems in quantum mechanics, all these answers will be given by solving the Schrödinger equation, which I'm writing now in the Schrödinger picture, which of course in general is a very difficult thing to do. Physically, what is happening is that at early times, I prepare the state in some eigenstate of the Hamiltonian, which is lambda naught. But since the Hamiltonian is an explicit function of time, the system will get excited at some intermediate time. So even though the state is, and I'll make all these statements very precise, even though the state is a nice eigenstate at early times, the state at late times would be very complicated. And we would like to learn about this state. This kind of question appears in many areas of physics. Of course, this is a very central question in non-equilibrium statistical mechanics. So it's of importance to condensed matter physics and cold atom physics. It appears in questions in particle and nuclear physics, and as well as questions in cosmology. And I'll try to mention the various aspects of this now. In modern days, so one of the reasons why one would like to study this problem is the question of thermalization. Very roughly speaking, thermalization means the following. According to common experience, if I take a system like this room and light a fire in the middle of this room, and wait for sufficiently long time, the entire rooms get heated and there is an equilibrium resembling a thermal equilibrium at late times. So the question is, and one of the ways in which you can study the time evolution of a state, of a quantum state of the system to a state which resembles a thermal state is quantum quench. As I have indicated, what quantum quench does is to excite the system in some non-trivial way. And if the system itself is a non-trivial interacting many-body system, common experience tells us that most of these systems at late times will behave like a thermal state. However, in quantum mechanics, this is a subtle issue. And the reason why this is a subtle issue is because a thermal state is described in quantum mechanics by what is called a density matrix, which is mixed. What this means is that the density matrix rho square is not equal to rho. And unitarity of quantum mechanics implies a pure state. A pure state is a state like, a vector in the Hilbert space, like a normal quantum mechanics, a kind of states which we deal with, which has rho square equal to rho, cannot evolve to a state with rho square not equal to rho. If you're not familiar with ideas of density matrix, just do not bother. I'm not going to use them. But I just wanted to mention that what we usually call a thermal state, strictly speaking, cannot be the result of a time evolution which starts from a normal state like an eigenstate of some Hermitian Hamiltonian. So one needs to understand in what sense is the state thermal. And this question has attracted a lot of attention over many years, particularly recently, over the past decade. This question has been studied very, very intensely, both theoretically and experimentally. The reason behind this very recent surge of interest in this kind of question has got to do with the fact that in cold atom systems, among others, the process of a time evolution under quantum quench can be studied experimentally in great detail. This is a huge advance over usual condensed matter systems, where the time scales are such that the time of relaxation to such a thermal state is just too fast for any measurement to be made. On the other hand, cold atom systems, there is a lot of control For example, a typical kind of system which you make is like ions in a harmonic trap. And one of the things you can do, so there's a harmonic oscillator potential. There are some ions in various energy levels in this harmonic oscillator potential. In fact, think of as a quantum eigenstate. And by time dependence, what you do is to change the frequency of this trap. This is typically achieved by tuning an external magnetic field. And then you want to see what happens to this set of ions. This can be measured. The second reason why this kind of process, quantum quench, is important has got to do with critical phenomena. In equilibrium, these are related to what are called critical phase transitions. And one of the major developments of the last century, one of the most important developments in physics over the last century, relate to understanding critical phase transitions in equilibrium. So one of the important reasons why this is important is because these transitions obey a property called universality, which is just a word by saying that many different systems behave similarly near a critical point. And the systems can be extremely different. For example, I can have a magnet in a magnetic field, or maybe at some finite temperature T equal to Tc, there is a critical point which is called the Curie point. Below T equal to Tc, this magnet is in some ferromagnetic state where there is a spontaneous magnetization. As you heat up a magnet beyond the Curie temperature, spontaneous magnetization is lost and it enters a paramagnetic phase. At T equal to Tc, there is a phase transition, which is an example of a critical phase transition, which is sometimes also called a second order phase transition. Or you can have a liquid gas system like water. And if you tune the pressure to a particular value, which is the critical pressure, and the temperature to a particular value, which is the critical temperature, so normal liquid gas systems display first order phase transitions. It's like if you heat up water and it starts boiling, it goes into steam. But however, it turns out that if you change the pressure and increase the pressure to a critical value, the type of transition becomes second order, which is the famous critical point of the liquid gas system. And this is also a critical point. And it turns out that the properties of a system like this are remarkably similar to a property with a system like this. Microscopically, they seem to have nothing to do with each other, but near the critical point, certain key properties are similar. The understanding of this rather remarkable universality has led to the renormalization group. Due to the work of Kadanoff, Wilson, and Fisher, and many others, a very important set of development in the 1970s. And in the course of these lectures, I hope to be able to provide you some of the basic physical principles behind this renormalization group. Now, as I said, critical phenomena in equilibrium. So I had given examples of critical phenomena which involve the temperature. But in recent years, it has been realized that there can be quantum critical points. These appear at zero temperature where a certain parameter of the theory, like a coupling, can be tuned to separate different phases. The understanding of universality in quantum critical points is somewhat similar to the understanding at finite temperature, and again involves the renormalization group. The kind of things which we will be interested in are typically quantum critical points. So critical points in equilibrium are quantum critical points in a time-independent situation is fairly well understood now. However, an interesting question involves whether there is universality when the time evolution, when universality in time-dependent situations, a classic example is like a magnet in an external magnetic field. Now, in the presence of an external magnetic field, and say at a temperature, so H equal to 0, T equal to Tc is a critical point. Now, suppose I place the magnet in an external magnetic field, which I change in time from a positive value to a negative value. So it's going to cross H equal to 0, and I keep the temperature of the magnet exactly at the critical, at that critical temperature. So it's going to cross H of T. Suppose it looks like some positive value and goes through a negative value, so minus H0, crossing H equal to 0 at time T equal to 0. So the time evolution of the parameter makes a system cross a critical point. So this is what we will call a critical quench, or quench across a critical point. And an important question to ask is that, does the subsequent time evolution of the system display universal behavior which reflects the universality of the critical point? This is a question which is very poorly understood, but there are tantalizing hints that there are certain quantities which do reflect this universality. And again, there are cold atom experiments which seem to show that this kind of universality indeed holds. So I'll try to explain some aspects of this universality. So let me point out the kind of areas of physics where this kind of process is important. I've already talked about condensed matter and cold atom systems. In nuclear and particle physics, this kind of process is involved in heavy ion collisions. When you collide two heavy ions in an accelerator at RHIC or in CERN, what happens is that the energy which you have imparted into the system, it makes the ions enter a phase which is sort of roughly called a deconfined phase, where there's a something analogous to a quark gluon plasma which appears. And this, of course, has been recently observed over the past decade. Now, this is a system which is clearly out of equilibrium, in the sense it's a highly time-dependent process. And many of the things which I'll be talking about has applications in understanding the time dependence in this process. I will not go into the specifics of such a process. This is just a kind of a motivational argument of why such a process is important. Once again, there are phase transitions which happens, which are not in equilibrium. It's time dependent, which one needs to understand. In cosmology, this kind of thing appears because the expanding universe provides a time-dependent background. Now, as the universe expands, it also cools. And as it cools, the universe is expected to undergo a series of phase transitions. And some of those phase transitions can be critical phase transitions. In fact, it is in this context that one of the earliest questions in quantum quench were addressed by Tom Kibble back in the 1970s, where he asked the following question. So as I said, that if there is a phase transition, there is some order parameter, some value of the Higgs field, for example, which will, as the temperature cools, the Higgs fields will try to align themselves in a particular direction. But however, as in a magnet, there will be regions or domains where inside the domain, the Higgs fields are aligned. However, the alignment can be different in different domains. So what this means, at the juncture of these domains, you have defects. Depending on the nature of the transition, these defects can be point-like, which are typically magnetic monopoles. It could be string-like, which are cosmic strings. Or there could be domain walls. In the 1970s, Kibble asked the question, can I predict, for example, the number density of such defects which are formed in this expanding universe without knowing much about the microscopic details of the system? And he provided a set of arguments which, looking back, don't appear to be very convincing, but the answers seem to be correct, that indeed you can, and showed that one can in fact do this. So one can predict, in fact, what is the defense density in terms of the Hubble rate of the expansion of the universe. This thing was later applied to liquid crystal systems by Zurek in the 1980s, and the result is a very famous thing called the Kibble-Zurek scaling, which I will describe in a lot of detail. Again, Kibble-Zurek scaling displays a kind of universality associated with critical points, but in a time-dependent situation. There is another aspect of this kind of process in cosmology, which which has got to do with finding models of cosmology in gauge gravity duality. This is a kind of project which I was interested in fact, in collaboration with Adel Awad, who is here, in a series of papers where essentially what appears to be a quantum quench in a quantum field theory appears as a cosmology in one higher dimensions. And many properties of the nature of this time evolution, we tried to understand the nature of singularities like Big Bang singularities. So I've just given a kind of a rough motivation to understand why this kind of process is very general, as a general interest in many areas of physics. In the rest of the talk, I will not go into the details of these applications very much, but I'll describe the essential physical issues and the physical problems and how they're addressed in some amount of detail. So this finishes the motivational and introductory part. So let me tell you a little bit of a plan of the lectures. So today I will introduce the basics of quantum quench. And I'll do this in just pure quantum mechanics, single particle quantum mechanics, not assuming much about quantum field theory, with a little bit of free field theory maybe. So tomorrow, I will review the basics of critical phenomena, equilibrium critical phenomena, and scaling and the ideas of the renormalization group, and how universality arises. And on the last day, I will put these things two together, and under universality in critical quantum quench. So I will start with number 1 now. So before that, maybe I'll ask if somebody has any question or comment. Okay, very good. In discussing the problem of quantum quench, I'll start with a very simple example, which all of you must be familiar with in your first course in quantum mechanics. And this is a harmonic oscillator. I'll, however, deal with the harmonic oscillator with a time-dependent frequency. So the Hamiltonian, for simplicity, I put the mass parameter to be 1, is given by P and X are operators, and omega of t is some time-dependent frequency. For example, omega of t, it can be like that, it can be like this, or many other kinds of profiles you can think about. Later on, I'll solve some very specific omegas of t's exactly to understand some basic features of the problem. What we want to do in the Schrodinger picture, where I have a wave function, which is a function of time, or a ket vector, which is a function of time, I want, of course, want to always solve the Schrodinger equation. And in the Heisenberg picture, I want to solve I might get my signs correct or not. I mean, I don't know, this could be a minus sign here. I want to solve the Heisenberg equations of motion. In the Heisenberg picture, the state is, of course, not time dependent. The state is whatever it is. It's the operators which are functions of time. In this problem, let me first discuss what is the situation in the Heisenberg picture. In the Heisenberg picture, there are two equations for the operators x and p. The first equation just tells you that the momentum operator is the time derivative of the position operator. The second equation tells you that the time derivative of the momentum operator can be written in terms of the position operator and this time dependent frequency. So putting this together, I have an equation, and because it's an harmonic oscillator, this equation is basically the classical equation of motion with x being replaced by the operator x. So we want to solve this equation. And in this case, solving this equation is quite trivial. So how do we solve this equation? This is the way of solving this equation. I'll explain the notation. And of course, P of t is the time derivative of x. So it's like f dot. A and A dagger are operators which have the commutation relation, which is 1. F is a function which satisfies the classical equation of motion. And this equation of motion ensures that the Wronskian, which is F, is a constant. And if I choose this constant to be I, this equation then ensures the canonical commutation relations of the x and p. So we want to find solutions to this equation F, complex solutions to this equation F. And once I find a set of solutions, I have a quantization of the problem. But of course, the whole point about doing this is to choose what are the initial conditions. Just to orient what we are doing here, let's take the example which will be very familiar, where omega is not a function of time, just omega naught. What would f of t be? F of t would be the standard function. And if you substitute this, you will recognize the standard solution of a harmonic oscillator. When omega is not a constant, the choice of these functions f and this complex conjugate depend on the choice of the initial conditions. So let me now illustrate this by solving the problem in an example which is called a sudden quench. A sudden quench is a frequency which changes suddenly at a time t, which I am chosen to be t equal to 0. So it was omega 0 for t less than 0 and omega 1 for t greater than 0. How do I solve the problem? I know how to solve the problem for t less than 0. It's a harmonic oscillator with a constant frequency. So the solution will be a general solution of the problem can be written as e to the I like this. And the initial condition would be that f of t, in fact, should be the standard solution which associates positive frequency with A operators, negative frequency with A dagger operators. So that means I need to choose A equal to 1 upon square root of 2 omega naught, and B has to be 0. This is called an in state. It's called an in state and it's written like this. What this means is that the state that this particular harmonic oscillator at t less than 0 was prepared in its ground state. So the system is in ground state at for t less than 0. I'll more precisely define what the state is. Okay. How do I solve it for t greater than 0? For t greater than 0, this is a harmonic oscillator with frequency omega 1. So the general solution will be this. And how are the constants A1 and B1 to be determined? They are determined by matching the solutions at t equal to 0, which means, so this call it f greater, let's call this f less. I want to require f greater at 0 to be equal to f less at 0, and f dot greater than 0 as f dot less equal to 0. This is because the equation which is satisfied by f is the second order differential equation, which is this equation. And this equation precisely tell you what the matching conditions are. Doing this, I'll just tell you what the answer is. It determines this A1 and B1. So it determines A1 and B1. And at the end of the thing, I have what is called the in solution, which is given by this. I strongly suggest that the students, to just do this exercise. It's a very simple exercise, but it's a very useful exercise to do. Very good. So once I do this, I can now go back to the operator solution of the equations of motion, which I'll call this. Okay. And the state I am interested in, so the initial state or the Heisenberg picture state which is the ground state at t less than 0 is given by A in annihilating the state. See, for t less than 0, it's a harmonic oscillator with frequency omega naught. So this is what describes the ground state. You could have prepared the system in some other state, some other eigenstate of the Hamiltonian, but I'm not going to do that. So let's see what happens in this particular state. In the Heisenberg picture, you can, once you know what these F ins are and what the solution X hat are, you can calculate anything you like. In particular, an interesting thing to calculate is what is called a correlation function in this in state. How are you going to calculate the correlation function? It's very easy. Just use this expansion, X hat equal to whatever, and just use the fact that A in is 0 and the fact that A in and A dagger in commute to 1. So let me give you what the result is, because the result is actually interesting, as we will see. Sorry, G plus. Now, if I had a time translation invariance, which would mean that there is no explicit time dependence of the Hamiltonian, such a correlation function has got to depend only on t minus t prime. But this is not a time translation invariant system because the frequency is a function of time. This is why there is a piece of this answer which depends on t plus t prime. So the whole answer depends both on t and t prime. And this is the answer for t prime greater than 0. You have broken the time translation invariance by changing the frequency suddenly at t equal to 0. Okay. It is instructive to compare this with a harmonic oscillator with frequency omega 1, which is the frequency for t greater than 0 at a finite temperature. T, which is 1 upon beta. I'll just tell you what the answer is. The answer is if you are not familiar of how to do this calculation and you want to learn how to do this calculation, just ask me. It's again a very easy calculation to do. The answer is given by this. You can recognize the Bose factor, the statistical Bose-Einstein factor, 1 upon e to the beta omega 1 minus 1. And if you look at the time dependence, you see that the time dependence of these two terms are precisely like the time dependence of the first two terms in the answer for the Quench problem. This is not an answer to the Quench problem. This is equilibrium statistical mechanics. You put a harmonic oscillator at finite temperature. Very soon, you will see the relevance of why I wrote down these two answers. And this has got to do with using these answers in free bosonic field theory, quantum field theory. So we're going to take a free quantum field theory in some number of dimensions with an action which is given by this. the standard action. But it's an unconventional part that the mass is depends on time. Okay. I want to canonically quantize this theory. And the canonical quantization now, a free bosonic quantum field theory is nothing but a collection of infinite number of harmonic oscillator. Each harmonic oscillator is labeled by the momentum k in the d spatial dimensions. So canonical quantization would be like this. Again, this is Heisenberg picture. Now there is always a label k. This is a Fourier transform plus its harmonic, this Hermitian conjugate. What are these f of k's? These are solutions of the equation and omega k square of t is nothing but k square plus m square of t. This is the breaking up of a quantum field in terms of harmonic oscillators. So as you can see, if I know how to solve the oscillator problem, I know how to solve the problem for free quantum fields. Okay. So now let us consider a mass which changes from m equal to m0 for t less than 0 to m equal to m1 for t greater than 0. So what this means was that this will be k square plus m0 square, which I'll call omega k0 square for t less than 0, and k square plus m1 square, which is omega k1 square for t greater than 0. So for each momentum k, it's precisely the harmonic oscillator problem which we solve. And since we know what the solution to this is, I can go ahead and calculate an interesting quantity, which is again the in-state correlation function. This is an integral over momenta. And that answer which I had for each of these harmonic oscillators. And finally, the term which breaks very good. This answer is, of course, basically lifting the answer which we got for the Quench problem, which was in this slide, and then summing over the momentum k. So not a big deal, but something interesting happens at late times. So late times when both t and t prime are very large compared to omega 1k, but when t minus t prime multiplied by the corresponding frequency is finite, then this object, which is cosine 1k t plus t prime, has very rapid oscillations. Because this object is large. When this object is large, then it, as you go over case, it sort of goes positive and negative very, very, very rapidly. As a result, because there is an integration over k, there are as many negatives as positives. So because of the integration over k, this term vanishes on the, this term becomes basically zero on the average. It's like as you sum over k, for one value of k, it's positive. So the next value of k, it is negative. And so when you do that integration, they just cancel out with each other. So as a result, in this large time limit, the answer for this correlation function is basically this part. Now compare with the thermal answer. With the scalar field at a temperature T, which is 1 upon beta. The answer for that correlation function is just again an integral of the answer for a single harmonic oscillator. So let me write down what that answer is. This looks very similar to these first two terms. There's an e to the minus I omega t minus t prime. There is a cosine of omega t minus t prime. But of course, this one is not an answer for any quantum quench. It's an equilibrium answer, which is characterized by a temperature, which is 1 upon beta. You can compare these two answers, and they are identical to the Quench answer. If I choose beta such that, and you will immediately realize why I put a subscript k on beta, by 4 is equal to just this. Again, a very useful exercise. Very good. So it appears that the correlation functions look very similar to correlation functions in equilibrium at a temperature, but the temperature appears to be different for different modes. Beta is k dependent. But that is not what should happen if this was really a scalar field theory at some temperature. the temperature would be just the temperature, the same for all modes. So this is not thermal. In fact, you don't expect the theory to be thermal because it's a free quantum field theory, and it is well understood that thermalization, namely something which looks like an object at a finite temperature, can only happen because of interactions. Nevertheless, something very interesting happens when I have a critical quench. A critical quench has M0 not equal to 0, but M1 equal to 0. So you start from a massive theory and you quench down to a massless theory. Why is it called critical? Because remember the relationship for the effective frequency of the harmonic oscillator with a mass m and the momentum k. This is, of course, the energy. This is what happened. Oh, wait a moment. This is the energy dispersion relationship. So when mass is 0, the energy has no gap. The energy just starts at 0. What is the 0 energy state? A state with 0 momentum. If the mass is non-zero, the lowest energy state has an energy which is equal to the mass. So that is why I'm calling this a critical quench. The final values of the parameter correspond to a theory which has no mass gap. As we will see, this is also something which characterizes a quantum critical point. But let's proceed and see what the answer for a critical quench is. This K-dependent temperature then has a following expansion. Something happened. Wait a moment. And the interesting thing is that the limit of very low momentum, I have a finite value of beta, and that value of beta is simply 4 upon m0. So even though the full system is not really thermal, but the low momentum correlators appear to be thermal. And the low momentum correlators are the one which will dominate for long distance correlators. So long distance correlators behave like thermal correlators. Okay. Can I take another 5 minutes?
Yes, yes.
Okay, good. Very good. What is the nature of the state? Remember, we are talking about the Heisenberg picture. So the state is whatever it is. It's what we call the zero in. However, it's interesting to look at the state from the point of view of the harmonic oscillator. So again, go back to harmonic oscillator with a time-dependent frequency. My pen is somehow, just 1 second, I have to redo the, okay, I'm sorry to do all this. So what is the nature of the state in terms of the harmonic oscillator for t greater than 0? So from the point of view of the harmonic oscillator at t equal to 0, which has omega of t equal to omega 1, the state in is a highly excited state. And let me try to explain what do we mean by saying that it's a highly excited state. What we mean is in fact the following. Recall there was an equation which we solved to solve the problem, which was J's, and we chose a solution such that f of t was for t less than 0. And the solution for t greater than 0, you had no control over. It is determined by matching at t equal to 0. The reason why this is a natural solution is because it corresponds to notion of what are the energy levels and the state for the harmonic oscillator with frequency omega equal to omega 0, which is the frequency for t less than 0. So that is why I call them F in. But I could have also done something which is natural for the harmonic oscillator with frequency omega 1, which is the frequency at t greater than 0. Or in other words, there is another solution which I call F out, which has the property which is 1 upon 2 omega 1 for t greater than 0. And once again, I can determine the full solution, which let me write down what the full solution is. For t greater than 0, and of course 1 upon 2 omega 1 for t less than 0. And I could have found a solution to the Heisenberg equations of motion by expanding in terms of these modes. Okay. Now, clearly, F in and F out are linearly independent solutions of the same differential equation, which is a linear differential equation. So they must be related by a linear transformation. And in this case, you can determine what these alphas and betas are very, very quickly. So let me write down what the answers are. Okay. Just as there was an in state, which was defined by this A ins annihilating the state, there is also something which is an out state, which is given by this. Now, the out state is a state which corresponds to the ground state of the oscillator, which for the oscillator with frequency omega 1, which is the frequency for t greater than 0. So we would like to know that how does 0 in look like in terms of the states of the harmonic oscillator with frequency omega 1. You can solve this problem by using the fact that these two modes are related by this transformation, which would mean, in fact, that these operators E are also related by a transformation. It's again a simple exercise to show that what this means is this. And then the equation becomes and you can solve this equation to yield that 0 in has an expression so this expression then shows something again happened. My pen is malfunctioning today. I'm sorry. I have to reload this again. Okay. Okay. So this state 0 in is a highly excited state. Of the harmonic oscillator at late times. In fact, this is an example of what is called a squeeze state, which is of great use in areas like quantum optics. This kind of transformation between modes or between operators is called a Bogolubov transformation. And the presence of these Bogolubov transformations are key ingredients of phenomena like Hawking radiation from black holes or particle creation in cosmology. The reason why it is significant for particle creation in cosmology is that we just showed that an harmonic oscillator, which was initially in its ground state, becomes such an excited state at late times. And if I think of these harmonic oscillators as the harmonic oscillators which come in a quantum field theory, excited states of harmonic oscillators are particle states. Like in a state like E dagger K on 0. So in quantum field theory, E K dagger is 0 is a single particle with momentum K. A state with A K dagger square of 0 are two particles with momentum K. A state like AK1 dagger, A2K dagger of 0 are two particles with momentums K1 and K2. So what in the field theory, what we have done is by the Quench process, we have come to a state which becomes a state with an indefinite number of particles of various momenta. And this phenomenon, this very simple phenomenon, even in free field theory, is at the heart of cosmological particle production. And as we will see in the following lectures, this kind of process is also at the heart of understanding late time states in a general quantum quench in many body systems. Okay, I think I will end here. So tomorrow I'll discuss the basics of critical phenomena in equilibrium, and you will already see that why this is actually important in a discussion of quantum quench. And one of the early indications of what we found is that when you have a critical quench, which involves a quench which goes to which crosses or approaches a Hamiltonian which is gapless, is something which we will see is what is associated with a quantum critical behavior, and we will start seeing universal features appearing in such quantum quenches. Okay, I'm sorry I took a bit of an extra time, but I'll be happy to answer questions.
Question? It's the end of the day, so I'm tired, I guess.
I'm sorry I couldn't.
Just say it's the end of the day, so maybe they're a bit tired. So
Oh,
think about it.
Of course, they are very tired. That's okay.
You can, I guess, Mahmoud can make the recording available if you guys want to take it. There's lots of very interesting basics.
Oh, thank you. Okay, in that case, see you tomorrow.
Okay,
See
thanks
you.
a lot.
Thank you.
Thank you very much.
Okay.
Okay, bye.
All right.